You learned a lot about the JavaScript syntax, the core JavaScript features, and how to write amazing JavaScript-driven applications, both on the front end, so in the browser, as well as with Node.js on the server side. Now, one topic we haven't really touched on thus far, or haven't really talked too much about, is security. And of course, security matters. In this module, I want to highlight what you should watch out for when writing JavaScript code, and some common pitfalls or some important things you need to keep in mind to ensure that your code is secure and you're not exposing security relevant data or anything like that in your scripts and so on. Specifically, we'll have a look at potential security holes and things to watch out for when writing JavaScript code. I'll of course also let you know how you can protect your code or which steps you can take to ensure your code is protected. We'll have a look at some common attack patterns or security concepts like CORS, which I already talked about, but which I will repeat here, CSRF, and most importantly, XSS, which stands for cross-site scripting attacks. And I'll also have a look at NPM packages or third-party libraries in general again, because these, as it turns out, can also lead to security issues. So now let's not waste any time, and let's have a look at what you should be aware of and how you can secure your code. So what could go wrong when we write JavaScript code or when we expose our JavaScript code? For that, we also have to differ between writing code that runs in the browser and writing code that runs on the server. And I will start with something that is only relevant if you're writing browser-side JavaScript code. And that would be security details in your code or private information in your JavaScript code. We'll also have a look at cross-site scripting attacks though, which is also relevant for browser-side JavaScript code. I'll briefly touch on cross-site request forgery or CSRF attacks, which is related to both front-end and back-end code, but which only works or only is a thing if you have some backend you're sending data to, and therefore I'll briefly talk about that as well. And I'll revisit this concept of cross-origin resource sharing we already talked about earlier. So let's start with the security details in your code. What do I mean with that? The important thing to understand about JavaScript in the browser is that your JavaScript code is part of what the browser downloads and runs, well, in the browser. So all your code runs on the machine of your page visitors. And it's important to understand that your JavaScript code can be read by them. Anyone who's visiting your page can read your JavaScript code that runs on this page. It's not hidden, it's not compiled to some unreadable machine code. It's totally available to anyone visiting your page, and that is super important. Therefore, any security relevant details you have in there, any confidential data you have in there, is exposed to your users, and therefore it should not be in there. You should not have security relevant information or confident data in your client side, in your browser side JavaScript code, because attackers may be able to abuse that exposed data. For example, if you have your database credentials in there, attackers could read them and could connect to your database to then read your data, change your data, or do whatever they want to do. Or if you're storing some client-related data, so about all your users, not just this user who's visiting your page, but all users of your page. If you have something like this in your browser-side JavaScript code, well, then anyone can read it and you might expose information about other people to all users. So therefore, because of this database example or any other data that might be confidential, you should ensure that such data does not end up in there. And let me show you what I mean. I'm back in our practice application we wrote, so this application. And you might remember that in the debugging section, we had a look at the sources tab, and there we actually could read the source code of this page. Here in the assets scripts folder, there it is. Now, of course, here we're seeing the code after Webpack worked on it. This is the code in development mode, and therefore if you scroll enough at some point you will find your actual code, and it will be quite readable because it's not minified, because it's not optimized at all. So all of this actually will be quite accessible and quite readable if you scroll down far enough. And therefore, anything you have in there is exposed. For example, if I scroll all to the bottom, where our script code should actually be found, we see here it's hinting at location.js, and if we scroll to the right, we actually find our code in here. This all inline code, that's our code. It's of course a bit hard to read, but it is readable. And it's not just us who can read that. Anyone visiting our page can read that. Now, once you build for production, this will be optimized and it will be more unreadable, but there are tools to make it a bit more readable. Actually built here in the dev tools. If you click on Pretty Print, this code is formatted such that it's a bit easier to read if it were minified. And besides that, if someone is really interested in getting your data, there are certain pieces of data, like your database connection string and your password, which is just a string, which of course will always be the same string, no matter if the other code is minified or not. So such data can be found and can be used. So any data which could be abused by other people should not go in there, should not go into your client-side JavaScript code. Now, in this project specifically, you might be wondering about things like our Google API key. Isn't that, for example, a security relevant detail? Well, it could be, but in Google's case, or in the Google API key case here, you can actually restrict the usage of that key in your Google Developer Console. There, you could restrict that only certain IP addresses can use that key, so that only the IP address where you are hosting your application can really send requests with that help of that key. And if anyone steals that key and tries to use it, Google will block requests by that person's IP address. So this is some security mechanism which a lot of APIs offer if you use their API keys, and therefore this is not a security relevant detail. That would be a different thing though, if we would expose data from our backend from this Node.js application. Now keep in mind here, I loaded a different project. This is the Node.js application we wrote, and there, for example, in the location.js file, we are connecting to the MongoDB database. Here I got my password and my username I used there. Now, this is data which is not exposed to our users because this is now actually only running on the server through Node.js. This runs on a machine and the user will never be able to see that code because this JavaScript code is never sent to the user. It's never attached to the outgoing HTML page. It's not loaded by any outgoing HTML page. So this code here is secure. It runs on a server, and unless users can access our server, which of course requires them to effectively hack our server, they can't read that code, so this code is secure. But if this code here were in our client-side JavaScript code, so in the code which is loaded by the browser and which the user can see, then users could see that data and abuse it. So long story short, don't put any important confident information into your client-side code. Users can read it, and there is absolutely no way for you to avoid that. You can make that code harder to read, you can minify it and so on, but it will always be readable and people can therefore read it. So don't put important information into your front-end code. Now let's move on to the next attack, which is the most dangerous attack, or the most dangerous attack pattern you can expose in your client-side JavaScript code. And I'm specifically talking about the client side, so about the side which runs in the browser, because the server side by default is way more secure. And when we talk about server-side attack patterns, they are not specific to JavaScript, whereas cross-site scripting and exposing security details is. So for the server side, there is a different range of potential attacks, one of them being CSRF attacks, others being SQL injection, for example, if you use a SQL database. And I'm not talking about them here because they're not primarily related to JavaScript. In my Node.js course, which talks way more about server-side code writing and so on, I do talk about more security holes you could expose on a server in general. So back to the JavaScript specific ones, and they are to cross-site scripting attacks, also shortened or abbreviated with XSS. This is an attack pattern where malicious JavaScript code gets injected into your application and is executed there. Now I'll show you an example for this because it can sound abstract at first, but this is really a dangerous attack pattern. You have to imagine if people are able to add code to your application, which all users of your application therefore execute, they are effectively executing code on the behalf of these users and at the same time on the behalf of your application on the machines of those users. And your code can do anything the code you write could do as well. So your code could send requests to certain domains, which might allow access by your application with the right course headers. The code might read the local browser storage of the user and send that to some server of the malicious user who injected the code, and much more. If you're able to inject JavaScript code into another page so that it runs for every visitor of that page, you're able to gather a lot of data about these visitors, potential security relevant data included, and you're also able to fake a lot of things and send a lot of requests maybe to your own malicious pages on the behalf of the application and on the behalf of the users visiting that application where you injected your code into. So that's really dangerous. You got full behind the scenes control if you inject code into another page. An example for that would be unchecked user-generated content. And I want to show you that example so that you understand what the problem is. When we talk about cross-site scripting attacks, let's go back to our application here, to this share a place application. And there, let's generate an address, 6th Avenue, find that place. And then we have this shareable link here. This is the link which does not use our backend code with a database, but which encodes all information into that URL. This attack pattern would also work with a backend database though, and I will come back to that in a second. So here we have this link. We can visit this page and we see this page here. So that's of course not too fancy. How could this be insecure? Now if we have a look at our code, there we have the myplace.js file, and this is the file responsible for displaying the page and this title here on this page once we visit this link with the encoded information. Specifically there, we set the title text content to our address. Now what if we would set not the text content here, which just sets the text node, but inner HTML, either as a mistake or because we actually do expect address to be more than just a plain string, which it is in this application, but which it might not be in all applications. And therefore, since this might be HTML code we want to output, we want to set inner HTML to not just render a text node, but all the HTML code, which is inside of address. And if I do that and I save that and reload, get the same output as before. However, if we inspect this in the developer tools, keep in mind, we're setting the inner HTML code of the h1 tag, and what we set there is in the end what we send to address, which is currently this part of the URL. Now, what if this part were actually a script, however? What if I prepared a URL, which I want to share with other users, which contains a script as the address? And not every user might carefully look at that URL, and therefore this might not be seen by all users who visit this page with whom I share this link. So there I could try to run an alert where I say hi there and hit enter. Now what you see is now this is injected here. Now we don't see a title here. Instead we see the script was indeed added here because I'm rendering this as inner HTML. Now you also see it doesn't seem to execute though, because actually modern browsers have a security mechanism where they don't execute script tags which are output with the help of inner HTML. Because of this exact scenario that you try or that someone tries to abuse a security hole in your application and inject JavaScript code which executes on your behalf. Also keep in mind that normal visitors of the page, of course, would probably not see that. They might wonder why they don't see a title, but they don't typically check the developer tools to see what's in there. So they might not see that. Now still, this doesn't really seem to hurt us. It's certainly unexpected, but since the browser doesn't execute the script, we're fine, right? Well, turns out there's more than one way of executing script code. Besides these script tags, which indeed are prevented by the browser to execute, what if we added an image here with a source that does not exist, and then an onError handler, where we then instead execute our JavaScript code. This is a valid HTML element. Now the source is not found, therefore on error should trigger, and we can add this kind of event listener to our elements. We as a developer don't want to do that because it's not really a good way of writing code, but as an attacker, it's great. We can add JavaScript code that executes right on an HTML element. If I now hit enter, indeed, we should see hi there, in Chrome at least. And we see that here because this HTML code is injected here. This image tag is injected here. The source is not found, so the onError handler executes, and therefore this script, this alert, executes. Now this alert, of course, is just annoying, but keep in mind I can share this link with anyone. I can post it in a Facebook group for people to visit it. And of course, an alert is not that dangerous, it's just annoying and unexpected. But here we could be doing other stuff too. We could be doing anything which might be security relevant. I could write a script in here, and yes, we can write a longer script in here simply by separating our lines with semicolons, where I access the local storage, read data from it, or read data from the local cookies, and send that to my own malicious server, for example. Visitors of the page will not see anything there. They don't get an alert, they don't get an error. I could even, if I'm really bad, in addition, render a h2 tag here with 6th Avenue. And then people might not see anything. If I now hit enter here, you don't get an error. Okay, I didn't format this properly, I should fix that. But other than that, the page works as it should. And here in the onError handler, in this script, we can do whatever we want as an attacker. We can steal confidential data from browser storage. We can send requests on behalf of the user who visited this page with this link to any backend we want. And that is therefore really, really dangerous. Here, this is a security hole we have in this application. We have this hole because here we're outputting inner HTML. Now, how can we fix that? One solution to fix this XSS security hole we have here is to use text content instead of inner HTML. If we do that and we visit this, you see now the code which previously was executed and rendered as HTML is now output as text, and therefore if we had any JavaScript code in here, like for example our alert again, where I say hi, would not execute. So now we automatically are not vulnerable to cross-site scripting attack. And if you never use inner HTML anywhere in your code, you of course rule out a lot of potential attack patterns. But with that alone, you're not totally safe yet. For one, sometimes you might need inner HTML, so then you need a way around potential malicious code. And in addition, it's not just inner HTML. If you're, for some reason, setting the onError handler of some HTML element dynamically to some user-generated content in some way, maybe you just want to have a user-generated text which is output in here, well, still then, whenever you inject any user-generated code anywhere into the DOM, this could be a potential issue. So you always want to make sure you either inject it as only text with text content, or if you set some other attribute of an element to some user-generated content, and potentially JavaScript code could execute there, like with these onError and so on handlers, then you want to sanitize the user-generated content before you output it. So for example here, if we really needed to use inner HTML, we want to sanitize the content before we output it here. Now sanitizing means that we strip away any JavaScript syntax we might have in there. That starts with simple script tags, but should also include common keywords like alert and so on. Now how can you work around the problem that you might need to inject user-generated content somewhere where JavaScript could execute, so you have no way of using a text content node here, for example, and you still want to make sure that the user-generated data you're getting here is secure and doesn't contain any scripts that execute? You can use packages like sanitize HTML. This is a package which basically helps you sanitize text and remove any unwanted tags in there so that invalid code doesn't execute in there. Now, one important note can be found here in the description right away. This sanitization actually should be done on the server if possible. That simply means that if we were in our Node.js application here, we might want to store any user input we get, so in our case the address, before we put it into the database. So we sanitize it with this package, for example, on the server side before we store it, so that the sanitized code is stored in the database. Because that's also something I mentioned. This attack pattern does not only exist if you can inject it into the URL, it also exists, of course, if you store something in the database. Because here I could be entering my malicious code like this, click find place, and if find place triggers our server to store this on the database, in the database, then we have a problem. So I want to make sure that whatever I send here is validated on the server before it's stored in the database. And you can do this with sanitize HTML as well. You can also use this in the browser, but that is a bit too late. It's not too late from a security perspective, but you still might have hacked or adjusted code in your database, which you also don't want. It doesn't do any harm there, but it's not ideal. If you ever forget to sanitize in a browser, you then have an issue. So try to sanitize on the server, not on the browser. Anyways, if you wanted to sanitize then, well, then you would just need to make sure you have this package installed, and you then can run the sanitize HTML function, pass your user-generated content, so the variable which holds the content the user has, to sanitize HTML, and then it will strip away things like that. It will ensure that this is not part of the output, that instead you are able to render HTML, but only secure HTML. This is what sanitize HTML does. Now, how do you use that package? Well, you can actually use the Node.js recommendation here, run this command here in your project. So I quit my dev server and run npm install sanitize HTML with the -- save flag. Now this will install it here as a dependency. And in my place.js, we can now import sanitize HTML from sanitize HTML. And now here, whenever we want to output or inject some user-generated content into an inner HTML tag or into another place where JavaScript could execute, we run sanitize HTML address in this case here. And if I do that, and then we restart the development server here with this added and the file saved, you will see that now if I reload this page here, the alert is not thrown. Instead, now I just have my header here, even though I still have my dangerous code in there, but that was stripped away by sanitize HTML. So just to show this again, if I remove that and we reload it, we get the alert. If we add it again and I save it, we don't get the alert. So now we protect ourselves against cross-site scripting attacks. Again, this is best done on the server before it's stored in a database. But in this example here, in this app where I don't have a server side, where it's all client-side code, where it's just data that's part of the URL, then of course, our only chance is to do that sanitization in the browser, and then we can do it like this, and we're now making sure that this specific cross-site scripting attack hole is fixed. So I talked a lot about cross-site scripting attacks, but this is an important and very dangerous attack pattern. There also is another way of launching cross-site scripting attacks, which is also important to be aware of and to keep in mind. Let's say you fixed all your holes in your code by either using text content or in places where you need to render HTML code by using sanitize HTML or something comparable. Now, you still might be vulnerable to cross-site scripting attacks. And do you have any idea where they might be coming from? How could someone still get JavaScript code into your page, which then executes when users load your page? Let's say you fixed all these holes where you output user-generated content, which is the number one hole. Well, how about third-party packages? In this project, I'm using the Google Maps JavaScript SDK, for example. I do have this import here. And what this does is it downloads a script written by a team at Google, which then also, of course, runs on the machines of my users. Any third-party JavaScript package you add to your project executes code when your app runs because you use the code of that package. In the case of Google Maps, we use it in the map.js file. There, we use that new Google Maps map thing, Where do you think is this coming from? It's coming from the Google Maps JavaScript SDK. So it is based on the JavaScript code we import from Google's servers. So we trust Google that their code is secure, because if it weren't, since this runs on the machines of our users, this of course would also be able to execute malicious code there. So when adding third-party libraries, you want to make sure that it's from parties whom you trust. For example, Google is quite trustworthy, of course, but you also, of course, need to be sure, or very sure at least, that these companies or library authors protect themselves against being compromised. You might trust Google, but if someone gets access to this code on their servers, which sounds unlikely, but if this is done by a frustrated Google engineer, let's say, then this person can, of course, rewrite this code which you import such that it still works, but that in addition to working, it does something malicious. So third-party libraries, of course, also can be hacked, and if they are, the malicious code that's injected into the library runs in your app and on the machines of your users. So you need to be sure that the libraries you're using are secure, that they're trustworthy, and that they're also defending against being hacked. So you want to make sure you're working with third-party libraries which are actively maintained so that security holes in the libraries are fixed, but at the same time where contributions, which in the case of open source libraries, which most libraries are, can be made by anyone, that contributions are checked. Of course, you can check the source code of the third-party library as well. And if it's a relatively straightforward, simple library, it might be worth scanning over that code and looking for anything strange. Does it try to access browser storage? Does it try to send HTTP requests, even though it's a library that shouldn't do that? Have a look at that and analyze that code. It might sound dumb, but this is a potential security issue, so you want to make sure you protect yourself against it. If you install something through npm, you also get a little hint. If I run npm install here to install all the third-party packages we're executing here, you'll see that once this is done, we get a little output here. Audited all these packages and found 0 vulnerabilities. Not every vulnerability it finds here is an issue though, and for some projects it will find quite a lot of vulnerabilities. It just means that there are potential security holes, which might also not be related to the code which is output to your users, but all these build tools which run on your machine and only on your machine as a developer, and therefore might not be as dangerous. But still, it just shows you that if there are vulnerabilities, you might want to check the versions of packages you're using and consider updating. Now again, you shouldn't freak out just because you find some vulnerabilities here, because most packages you use in modern projects only run on your machine. And of course, this is also not what you want, that you have a potential security hole there, but at least you're not sharing this code with all users of your web page. So therefore, this might not matter as much. And a lot of vulnerabilities are really just that, a vulnerability, not necessarily one which is getting abused at this point of time. Still, having a green 0 here is nice to have, but even more important is that any packages you use that end up in your code, like the Google Maps package here, that these packages are also trustworthy and secure. You never have 100% security, but you should of course aim for as much security as possible. So that were cross-site scripting attacks, the most dangerous attack pattern when we talk about JavaScript code. They only affect browser-side JavaScript code, but since this is the part where you typically run a lot of JavaScript code, it is a thing you definitely have to watch out for and you have to be aware of. Now with that, however, let's move on to cross-site request forgery. What is this attack? It can be related to cross-site scripting attacks, but it doesn't have to be. The idea behind cross-site request forgery is that people trick you into clicking on a link that leads to a prepared page where they abuse your local cookies to then send a request to the page you would normally talk to as well, let's say your online banking backend. But since you're coming from a prepared page, you then do something there automatically without you recognizing that you don't want to do. For example, send money to someone you don't want to send. Maybe that even is possible to happen behind the scenes without you noticing. So this attack pattern also depends on injected content, so injected JavaScript code, but it can also be just HTML content which submits a form to the trusted server. The problem is that the form is part of an untrusted page, which you might not recognize if the URL looks similar. And then requests on your behalf with your cookies can be made to the trustworthy server. So the only danger and the only problem is that this is all happening from a malicious site. So actions might be executed on that trustworthy page with your data without you knowing that it happens, and therefore you might want to protect against that. Let's have a closer look at this pattern, though I do talk about it in more detail and also how to prevent it in my Node.js course, because this is more a server-side issue. You need to protect against CSRF attacks on the server side by using a mechanism which is a CSRF token, and again, I do discuss this in my Node.js course where we work on the server side on the backend all the time. So CSRF stands for Cross-Site Request Forgery, and the idea is that if you're the user of a web app and you have some backend, let's say the online banking site which uses Node.js or any other programming language, this is not exclusive to JavaScript, uses any programming language and it talks to database, the server. Now you're visiting the front end of this page, let's say the user interface of your online banking site. And now when you have such a setup, typically the server-side application identifies you with a so-called session. So you logged in and then the server-side generates this session object, stores session data on the server and sends you the session ID which is stored in a cookie. That's a typical authentication setup you have in web pages where front-end and back-end work together. Now then you might be sending an intended request, for example to send money to B, and all is good. The problem is that if you now visit a fake site because someone sends you a link to it, which looks like the trustworthy site but which isn't, then you visit this page and there people send a request to the trustworthy backend. Therefore, the browser attaches cookies that belong to this trustworthy backend, which is your session ID, for example, and everything works. The problem just is, since you're on a fake site, the request might one that is intended by the fake site, but not by you. For example, to send money to C. And this request will succeed because you sent the right cookie, the right session ID, and you send it to the right backend. So again, more details can be found in the Node.js course, but this is also a potential attack pattern, but not directly linked to JavaScript. It can be implemented with cross-site scripting attacks, but it can also be implemented by using such a fake site, which does not require cross-site scripting attacks. So therefore, this is not really a JavaScript security thing, it's more a server-side or general web application security thing, and therefore I do discuss it in more detail in my Node.js course where we write a lot of server-side code. The last security hole you should be aware of, or the last security relevant concept you should be aware of to be precise, is cross-origin resource sharing, and I did talk about this earlier already. It's not really an attack pattern, but a security concept. The idea here is that requests from your browser-side application can only be made to a backend, so to a server side that runs on the same server, so that the HTML page and the script that executes there was served by the same server you're trying to send a request to. That's how browsers by default work with your pages. This is what they allow by default. Now, in modern web applications, you often need to send requests to other servers though. So a server which did not serve the running HTML and JavaScript code, but which only provides some API endpoints, some URLs to which you can send data, to store data, or to fetch data. This is something we had a look at in the Node.js module. Then you can control via server-side headers, and only via server-side response headers, whether this incoming request is allowed and you send back a valid response or not. So this is a concept where by default browsers would not allow you to reach out to some other server, but with the right server-side headers you can override this. So it's a concept which in the end should secure servers so that not everyone can access their resources, not every page can access their resources at least, but with the right headers on the server side, you can allow this. And an example for that actually would be JavaScript modules. This built-in JavaScript concept also required a development server, if you remember. And it required a development server because JavaScript modules, so JavaScript files you import into another file, are only allowed if they're from the same server. So I'm only used to import another JavaScript file which sits on the same server, which is served by the same server. And here we have no real way of changing this because that's a built-in security mechanism by browsers specifically for this JavaScript feature. Another example though would be the Node.js application we worked on. There we have our different routes which we handle on the backend, like add location, and the request which is sent there is not sent from some page that is served by the same server, it's sent by a page that runs on a different domain on a different server. And still it works because here I set these right course headers, which tell the browser that's okay, this page which sends the request is allowed to get the data, and therefore the browser won't block it. So it's a security mechanism which you can use or disable or configure to your needs based on your requirements. That's the idea behind CORS, this cross-origin resource sharing concept. This is it for this module. The two most important attack patterns or vulnerabilities I want you to take away from it are these two: security details in your code which you expose accidentally, and cross-site scripting attacks. These are the JavaScript specific attack patterns, whereas the CSRF pattern works with any language on the backend and with no JavaScript code in the frontend, and CORS is a general security concept. But the two leftmost holes, security holes, are the important ones you might have in your application. If you expose code there, all your JavaScript code is always readable by anyone. That's something you have to keep in mind. Exposing important information in your JavaScript code allows anyone to read and abuse it. And cross-site scripting attacks allows users to prepare data or prepare links which all visitors of your page might then see, and if that data, this prepared data, contains scripts that executes, then for all visitors of your page, these scripts will execute and can do dangerous stuff, like read personal data, send malicious requests with user data to some malicious servers, and so on. So you definitely need to protect against these two security holes, for example, by sanitizing output, by using text content instead of inner HTML, and by not leaving any important data in your JavaScript code.